what we had talked about last time, where we were talking about various kinds of adapters. So we talked about container adapters like stack and queue and priority queue. We talked about iterator adapters like back inserter and reverse iterator and those kinds of things. And then we were starting to talk about so-called function adapters, and that's what we're going to talk about today, function adapters. As we talked about, there's a couple different kinds of function adapters. We talked about binders, and we're about to talk about negators. And I think we'd gone through a couple of binder examples, and forget exactly where we left off. Here's a good one to talk about, though. So this will show a couple of interesting things. So here's an example where we've got a string with spaces in the text, so spaces in text, right? And then we go ahead and we use our good friend, the remove if algorithm, to go from the beginning of the string to the end of the string. And what we want it to do is we want it to remove any spaces in the text. So how are we going to do that? So there's various ways we could do this. One thing we could do is just say remove and then give the space character, so it removes spaces. But instead, we're going to be a little bit more clever, and we're going to use the remove if algorithm, which, as you maybe recall, anything with an underscore if suffix is a so-called predicate algorithm. And over here, we have ourselves a binder, which is going to bind the equal to functor, parameterized with character, to the space character. And so what that's doing is it's creating a unary functor, and when that guy's function is called, it's going to check to see whether whatever's passed into it is equal to the space character. So as you can imagine, what happens here is it's going to go here from beginning to end, and everywhere it finds a predicate that matches space, it's going to remove that, and when it's all done, it'll give you back an iterator to the new end, having moved stuff over like we talked about before. And then when we're done, we say, hey, please go erase yourself from the new end to the old end, and that'll free up any space. It'll give the container the option of freeing up any space and deleting those items. Patrick? Typically, you'll use binders when you have when there's a binary functor that already exists that does what you want, but you're using it in a context that expects a unary functor. So equal to is a binary functor, but remove if expects a unary functor. So in order to get a binary functor to work like a unary functor, syntactically, we have to bind it to something that's a constant, in this case, the space character. Yeah, good question. Other questions about that? Here's another example. Here we have another vector. We put a bunch of things in the vector. We go here and we first try to remove, we first count to see how many things in the vector are greater than 5. And here's the funny part about STL. When you first see this stuff, it's like, how do I even know how to read these expressions? They seem sort of inside out, if you will. And that's kind of how you read them. You look at this thing and you go, okay, it's a predicate algorithm. And once you kind of know algorithms, you kind of expect to see a range from beginning to end. So that's pretty straightforward. Okay, it's an algorithm. It goes from the beginning to the end. It's a vector. I get that. That's easy. It's going to go through a range, the whole range. And then you go and you look at the third parameter, which in this case is expecting to have a unary functor. And this guy says, okay, it's a binder, so I'm going to create a unary functor out of a binary functor. And the binary functor is going to take the greater functor. The binder function adapter is going to take a binary functor called greater, the constant 5. It's going to make a new anonymously created functor, which is a functor that's a unary functor that has an instance of the binary functor and the value 5. And then that guy's operator function call algorithm will be called by countif when it wants to check to see if the value in the range succeeds or fails with respect to the predicate that it's calling. So you can just kind of read it from the inside out. So it goes through and it finds out how many values are greater than 5. In this case, as you can see, 7 and 8 will be greater than 5. And then we go through and we're going to remove anything that's less than something or other. Let's see, less than 4. So we make a new functor that has a binder that binds the less than operation and the value 4. and we go ahead and we remove anything that matches that. So we're going to remove the 4 values. Yes, sir? Yeah, okay, good question. Let's go ahead and show the answer to that question. The question was, can you use a variable here instead of a functor? The answer is absolutely yes, but let's take a look and I'll show you. Prove it to you. Maybe I will. There we go. All right, so let's cut and paste this guy and stick him over here. Okay. And decolorize him. Hopefully that's still big enough to see. I think so. Okay, so I think what your question was is that could I make this guy, could I say standard bind second binder? Let's call him, give him some name like greater than 5. So we could do that. That would be perfectly acceptable modulo the inevitable syntax error that's probably creeping in here. Probably have to do something like this.
You don't have braces around your main.
Which one?
Around the whole function main.
What's the problem?
Oh, we can't see them.
Oh yeah, it's come on here. Move him over so you can see it a little better. There. So we will take that on faith that that compiles. I don't want to compile it right now, but yes, you could create an instance if you wanted to. No self-respecting STL program would ever do that, but you could do it. Yeah. Oh, could it be a variable? No, it has to be well, it could be a variable, but it's going to take the value of the variable and bind it at that time. Yeah, I think what your question is, could you say something like, n, where n would then get, you could reset n and every time through would change. No, it has to be something that resolves to a constant. It'll copy the, yes, if it is a variable like n, it'll, just to be very specific, you could say, int n equal 5, n, and that'll work just fine. It's just it'll make a copy of it, and it'll stay set through the whole use of it.
Could you use the auto syntax with remove it at all?
That's a good question. In fact, let's have some fun with that. We're probably getting ourselves down a rat hole, but what the heck. Yeah, look at that. All right, now I don't have to think about the syntax anymore. That's great. So you can see it actually works. Was there another question stemming from any of this stuff? So bottom line, you can't, whatever you bind it to has to stay bound. Oh, you'd asked if I could use the auto down here, like this, right? Like that? Yes. So you get a pretty good idea why auto is useful, right? Because there's a lot of gobbledygook you otherwise have to write that you no longer have to write.
Instead of use pushback, do we use back inserter?
Oh yeah, you could. I just use pushback to make it simple. I could also, I could do something like this. I could say for int I equals 0 or 1. I less than 10 plus plus I, and I could say back inserter oops. Well, actually, you wouldn't do that. You would just basically say, v dot pushback I. That's another thing you could do. So I mean, you could use back inserter, but it would be overkill for something as simple as this. You would typically use back inserter if you were using like the copy algorithm or something where you had an output iterator and you were trying to add things to it where you didn't know its size.
What's the difference between a binary functor and unary?
Whether they take, the question is, what's the difference between a binary functor and a unary functor? Judging by the names alone, unary functor takes one parameter, unary. Binary functors take two. So like equal to, that takes two. That'd be a good example of a binary functor. You know, is negative, that'd be an example of a unary functor, or negates would be another example of a unary functor.
Is there, does auto use runtime type?
No, auto is resolved at compile time.
So is there a, I guess, is there kind of a limit on how frequently you shouldn't just use it everywhere, I'm guessing, but.
So the question is, should you get carried away with auto? Well, it depends largely on a couple things. It depends largely on whether your compiler lets you tell by hovering your mouse over the thing what its real type is. Because if it does, just use it wantonly, and if you ever get confused, you just put your mouse over there and go, what type is that thing? Oh, it's a iterator for a vector. If you're in 1980s technology like my Emacs program here, it doesn't do that. So the downside with using auto is, yes, it made it easier to not have to think very hard about what this is, but then I've also sort of forgotten what it is. Like, what the heck is that? Now, of course, a lot of times it doesn't really matter what it is as long as I know how it works. So I don't have to really know the details of whether this thing is a template parameter with an int or whatever. It just figured all that out on its own. But you can imagine in a large program where people were doing manual inspection on an airplane with no Wi-Fi connectivity or whatever, with a printout, it might get confusing. So I guess it's a little bit like using the using keyword. You know, you can go nuts with it and you can make your code really concise, but you can't really figure out what it does anymore easily without a lot of support from your underlying tooling.
Oh, I guess my question would be, like, looking down at the assembly code, you're not actually saving any code, are you?
You're not saving any runtime performance. This is purely keeping programmers from having to think about details that may be sometimes unnecessary for them to understand, which was really the question that was asked. When is it useful to understand details and when is it not? And there's no good answer, but the better your tools are, the more you can abstract. The better your tools are, the more you can have the extra levels of indirection pattern, right? There's extra levels of indirection going on here because the compiler is keeping track of type information for you, and you're able to use a shorthand for it without having to remember the details.
So when you're using a binder, you're basically like making like a hybrid method, I guess, or hybrid.
You're creating an object, usually anonymous, but as we just saw, it doesn't have to be anonymous. You're creating an anonymous adapter that takes something that requires two parameters and making it possible to use it in a context where you only need one. And the reason for doing that is to avoid having to write a special purpose functor that does what you already have with a general purpose functor, right? So we already have a functor that checks whether something's greater. We already have a functor that checks whether something's less. But they're binary functors, and they don't check for 4 or 5, right? So rather than writing a functor called checks to see if less than 5 or equal to 5 or whatever, we can use a binder to take an already existing thing and bind it with something else that we already have. Now, once you start getting lambda expressions, some of these things become less necessary, but it could still be useful for documenting what your intent is. Yes?
Corresponding bind first function to the bind second.
There's a bind first function that binds the first argument, bind second binds the second argument, as the name implies. Okay, other questions about binders? Next thing is negators and some pointer to function adapters. Let's talk about those briefly. So here's a little C++ trivia for you. For some odd reason, due probably to just being in a daze, not unlike looking at dozens of programs, after a while you just kind of glaze over a little bit. When the C++ Standard Committee put out, I think it was the C++ 2003 standard. It was one of the ones about a decade ago. They had intended to have a copy if function, but they left it out. So copy if would have copied anything that matched something. But instead they put in a remove copy if function. Remove copy if copies everything except something that matches a predicate. So if you needed to get copy if semantics, but you were stuck with a standards compliant C++ library that didn't support copy if, which is, they didn't need to support copy if. It wasn't in the standard after all, right? They forgot it and left it out during the typesetting. Then what you needed to do was you needed to use remove copy if in conjunction with a negator. And the negator would give you copy if semantics, right? So here's how this works. Here's remove copy if. We put a bunch of stuff into a vector, and then we go and we use remove copy if to go through the vector, v1, and we're going to store the output into v2 using a back inserter. And we're going to remove anything that's greater than 3. So that's what this binder does. It makes ourselves a new anonymous functor, unary functor, that is going to return true if this is greater, if the parameter in the vector is greater than 3. And since it's a remove copy if, it'll get rid of everything that's greater than 3. But if you want to copy everything that's greater than 3 as opposed to remove everything that's greater than 3, you're out of luck unless you knew how negators worked. And a negator is simply an adapter that takes a unary functor and negates its result. So if this thing returns true, the negator makes it return false and vice versa. Patrick?
If it's 2 arguments and it's greater, couldn't you use std bind first and then it'll return true if 3 is greater than
Let's just follow along with the example for now, and we'll think about other alternative ways to do it. I'm just trying to show why we could use negators in this case. So that's the only purpose right now. That's a good question, but I don't want to get distracted on this. So here's the negator. All I was trying to say is we already have a binder that does something, and now we want it to do the opposite. And so rather than rewriting the algorithm, instead we simply negate this expression. Now what's really going on here, if you think about what's going on here, it's kind of cool. Greater is a functor. The binder is creating an anonymous functor that holds an instance of the greater functor and a constant. And then that guy is then held inside another anonymous functor, which is going to take the result of calling the result of the binder, which itself calls greater, and negates it. So we're chaining these things together. And we'll show you another example in a minute that goes even further off the deep end. But they're basically chaining together all these different adapters in order to be able to get more expressive, correct result. Yeah? What's that? Good question. So the question is, why do we not use this? Well, let's see. It's not in my editor. So you want to be able to put like exclamation point standard bind second. So does anybody know why? Because it's the wrong time to negate. If you tried to negate it there, it would try to do it at compile time. It would like turn. Weird things would happen. Because it's what we want to happen here is we want to create a functor. It would probably be a syntax error, in fact. Just for kicks, let's see what happens if we do that. Yeah, I think it would get confused, but I want to convince myself what it does before I speculate on what it's going to do. All right, so here's what we want to do. First, let's make sure this thing compiles. And it does. And let's run it. And it works. And now let's break it. So basically, it's a syntax error. and the problem is that we're trying to create a functor that can be evaluated at runtime to negate something. Whereas what we would do by using the exclamation point, if it compiled, which it won't, is that would check sort of be more like it would compile at the wrong time. It wouldn't do the binding in the right time because it would be used in an expression syntax. I still don't think it would work, but just for fun. Yes, that's what it's trying to do. Yes. Let's see if they list operator overloading C++. I'm trying to find the definitive set of overloaded operators in C++. Let's see. Yeah, there you go. I think it's already overloaded. So, but it wouldn't work the way we want it to be working in this case. For the same reason why you can't pass in the less than operator. You have to pass in the functor less, right? Same basic reason. It's a syntactic issue. Here's another simple example. I'm going to go through this pretty fast. This is a class that has some member functions in it, and we want to be able to use the member functions in a context where algorithms are expected. So we have a for each loop, and it goes ahead and it wraps up the member function to be called here every time through. Pointers to functions and pointers to member functions are not the same in C++. All right, here's my favorite example. I gave you guys this one the other day just for kicks. I know people have been working studiously to figure it out. So here it is. So we have a vector of character stars, which is a little bit wacky because everything we've seen to this point have been classes. We've parameterized the containers with classes that had constructors and destructors and good stuff like that. Now it's character stars, right, which are pointers, and they don't have constructors and destructors the way that regular classes do. And then we go ahead and we push character literals, 1, 2, 3, 4, etc., into the vector. And then we go ahead and rewrite the output. And now what we want to do is we want to be able to find if the character string 3, the character literal as a C-style character string 3, exists in our vector of strings. That's what we're trying to do here. So the question is, what combination of adapters do you have to put together in order to be able to use a built-in algorithm like find to get the job done? So we're going to end up using findIf, which will go through the vectors. And here's the wonderful expression that it does. What it does is it takes the standard C function strcomp. Does anybody here remember strcomp? So what does strcomp do? It takes a char star, actually a const char star and a const char star, and it goes through one character at a time from beginning to null, the null character, and it basically subtracts the left from the right. And it checks to see what the results are. Do you remember what the output of strcomp is?
0 if they're the same.
It's 0 if they're the same. That's very good. And let's say, for the sake of argument, it's non-zero if they're not the same. It actually also tells you whether one is greater than the other too. It gives you greater or less than 0 as the result. But what's important here is that they return 0 if they're the same. Because when you subtract them, if they're always the same, they'll all end up being 0, right? So we have a pointer function that we use a function adapter to turn into a functor that can be used in the context of a binder. And we bind that functor to the character literal 3. And now we can go ahead and call this thing in find. But the problem is that strcomp returns 0 if it matches and non-zero if it doesn't match. But find expects to have true if they match and false if they don't, right? So what's the trick? Of course, you use a negator. So we negate the results of binding a pointer to function adapter to strcomp, which will then return true if we find something in this vector that has the same value that strcomp says is the same with the literal that we're looking for.
The negation inside find, like negate pointer funds strcomp before binding it?
No, I don't think so. You want to be able to put like not pointer fun. No, because in that case we need strcomp to take in the character literal in order to compare them. Danny.
The reason we use pointer function to convert to a functor is because we want to later end up using bind second, and we can't do that if it's not a functor. Is that correct?
That's exactly right. The binders and negators and binders, negators, and algorithms all expect to work on functors. They don't expect to work on pointers to functions. So we need to, or even if they do expect to work on them, they're not going to work on them in the right way in the context in which we're trying to use them here. Anyway, that's a really fun one because it demonstrates putting together pointer to function adapters, binders, and negators in order to be able to compare something using an existing algorithm. The goal of all this adaptation, good quiz question, what's the goal of adaptation in STL? It's to avoid unnecessarily rewriting code that can be taken off the shelf in the form of reusable artifacts, and then combined with a handful of adapters, like binders, negators, function adapters, and so on. Yeah. So the purpose of the purpose of adapters in STL is to avoid having to rewrite code from scratch manually. But instead, what you can do is take existing functors that already have a purpose and combine them in almost infinite ways without having to write much new code. You just combine existing stuff. So it's all about reuse. It's about reducing the surface area of your program's design and implementation space to a small number of well-understood primitives that can be rearranged in various ways. So it's about integration as opposed to creation. So rather than create something, you integrate what already exists. So yeah, so the point of adaptability is to not have to redo as much stuff. I mean, just take a step back. Remember the examples we talked about before of adapters from everyday life, the adapters you use when you go overseas to plug your alarm clock or your shaver or your computer into a wall socket. Rather than having to go out and buy lots and lots of new computers, clocks, shavers, whatever, you buy one adapter or maybe a handful of adapters or one adapter with many ways of shifting back and forth between different types of form factors. And then you use that one adapter for everything as opposed to having to get new versions. So the purpose of adapter is to let things work together that weren't designed to work together. So we've got all this stuff that already exists. We're going to make it all work together without us having to create new things. So it's the same basic idea of what you see in everyday life. It's reducing the amount of new stuff you have to create. Instead, you take what's already there and you assemble it. Anybody ever see the movie Apollo 13? Classic Tom Hanks movie. Remember, there's a scene in the movie where the carbon monoxide levels have gotten dangerously high in the lunar module, and they've got to find a way to reduce them, otherwise everybody's going to die, right? So there's a scene where there's a bunch of engineers like us sitting around a table, and a guy runs in, and he throws a bag full of stuff that you'd find in a spacecraft on the table. So it's like, duct tape, toothpaste, Tang, right? And he says, you guys have, 3 hours or whatever to take all this stuff and come up with an air scrubber that'll fit into this particular form factor. And if you don't, everybody's going to die, right? So that's what being an engineer is all about, okay? Working under pressure. Using things that you don't necessarily have the luxury of creating yourself from scratch, right? They had to take what they were given and do something really, really interesting and novel with it. So that's the adapter pattern, right? Those guys were like figuring out, okay, we can take this and we can shave that off and put this here and connect it together. That's a lot of what programming is. A lot of times in real life, they don't give you the chance to start from scratch. People don't say, oh, you're the new guy on the project. Why don't you rewrite the Linux kernel? Instead, they say, oh, you're the new person on the block. Why don't we give you the wonderful task of debugging this kernel driver, right? Except you don't get to write the kernel. You have to figure out how do you do this and how you fit into the constraints, which, by the way, a lot of the assignments we're doing in this class, and you'll see this as we evolve over time, they're trying to give you that experience in a microcosm, right? Where we're not going to make you rewrite the Linux kernel or even adapt a device driver, but you got to build a working array class. And you've got to use the working array class to build a working AQ class. And once you have a working AQ class, you use that to build something else, right? So every step along the way, you're taking what you got, you're adding a few things to it, but the things you already built have got to work. And what you're undoubtedly going to find in at least a couple cases is sometimes there are bugs that were lurking in your older stuff that you thought you could rely on, only to discover there was something that didn't get caught in the test cases, which is an indication of why it's important to have unit tests, but it's also an indication when something goes wrong that you're willing to be suspicious of lots of stuff, right? It's not just the new thing that you're working on that maybe have the bug, those things may get traced all the way back to the array class. And I've seen that many times in the class. Not a whole lot, but every once in a while someone has a really mysterious bug, and it turns out that, I don't know, their assignment operator in the array class didn't return star this. And so it worked for the test cases we gave, but then when it gets used later in one of the final assignments, it fails. And it takes a long time to figure that out, right? Because you don't expect it to fail. Yeah?
Why is the negator called not one?
Oh, there's two negators. There's not one and not two. Sounds kind of like a Dr. Seuss, like Dr. Seuss characters. Not one and not two. So we take a look at not one, not two. So there's not one. Yeah. And so as you might expect, not two is a binary negator, whereas not one is a unary, or it returns the negation of a binary function, whereas not one returns the negation of a unary function.
So
that's the difference.
If this were kind of disregarding find if,
Yeah.
if you had taken out find second, you would want to use not two here.
Modulo a bunch of other things, yes. So I absolutely guarantee we could find a use case where bind two would be, or where not two would be exactly what we needed. All right, there's a bunch of other little helpful utilities in STL that do some stuff for you. I'm not going to talk about those in much detail. Okay, so the next example, which I'm not going to go over right now, we may or may not go over it. It's a really cool example that puts a whole bunch of things together. And the thing that I had the most fun with this example, this example actually would have come in quite useful. Many years ago, this class is kind of at a weird time, most classes, as those of you who are trying to figure out when the final exam is, notice that there's really nothing in the course catalog about Monday, Wednesday classes. It's like Monday, Wednesday, Friday classes, which would go from 3 to 4 or something like that. 3:10 to 4:25 is weird. So because of that, one time they scheduled us in another classroom, and they started the class at like, I don't know, 4:10, right? Because they thought it would be open. And so we had a conflict. Well, this little program here looks for conflicts in schedules. So if you have a bunch of classes at different times, it'll tell you when the conflicts are. And it's all written in STL, and it does some cool things. And I'm not going to show it to you in detail right now. The one thing I was going to show you that's really cool that this thing does, though, it has an argv iterator. So remember we talked about argv before? Argv is those are the parameters that get passed to the command line, and it comes in the form of a count, which is argc, and an array of pointers to strings, or strings, it's C-style strings, which is argv, right? But the thing is, you can't really use it in a STL-like context because it doesn't work like that. So I wrote a little adapter that takes argv and argc and makes it work like an iterator. And so with this little adapter, which as you can see is just a page or so long, what I could do was I could take command line arguments passed in, and the command line arguments are passed in the form of something like this. So you pass in a whole pile of stuff on the command line, and those things are read by my little adapter, and, whoops, come on. And so my little adapter takes argv and argc and turns them into something that you can use with the STL algorithm copy to copy the parameters into a vector. And we'll come back and look at this in maybe at some other point. But the point there was that I've already got a great algorithm called copy to copy from something to another, but there was no way to go from copying argv argc into the vector I wanted to store stuff in. But no big deal. This is STL. This is C++. The solution is just to write an adapter. So I wrote an argv adapter, which allowed me to do that. So that's the cool thing. Once you start thinking in terms of the elements in STL, your programs become remarkably expressive. So basically what we did, we have a vector of meetings. A meeting just keeps track of the class times. We copy all the classes into this vector. We sort them. So we have a sorted vector of meeting times. And then we go through there, and we use the 5-parameter transform algorithm to start at the beginning and go to the end. And it looks for conflicts between two adjacent times, where a conflict is defined as them having overlapping start or end times. So, and then when you're done, you print the results out. So the cool part about this, without going into the details, is with STL, when you think about things in a generic programming-like way, you can write really concise expressive code where there's very little that you actually write. Almost everything is coming out of the STL algorithms and containers, and you're just kind of assembling the different pieces, putting them together, and then using them in a manner that's very efficient and very parsimonious, very simple. So we might have a chance to come back and talk about that later. Let me briefly talk about the next programming assignment, though. Tell you what, I will go ahead and all right, so here is the next chunk of stuff. Ignore the due dates for now. I'm just going to take them out for the moment because I haven't figured out exactly when they're due. But I will do that shortly. And I will try to avoid what I always end up doing, which is assigning the final due date during exam week, which is bad, so I will make sure not to do that because that's annoying. I hate that. So here's the next assignment. This assignment is really the bulk of the class. So everything you've done up to this point is just kind of a warm-up. For this, there are four parts to it. First part's pretty simple to implement. Takes a while to figure out how simple it is, but it's not a lot of code. Then after that, things get a lot more interesting because now we start doing patterns in great detail. So what we're going to do is we're going to use the adapter pattern, which we've been talking about many times before. And we're going to use the adapter pattern in order to build an adapter that will let us select at runtime between the AQ implementation or the LQ implementation. So right now, if you look at AQ and you look at LQ, they're just like STL types. They don't have any common use of base classes. They don't have any virtual methods in them. They're just classes out there that have an STL-like interface in some ways. In some ways, they're not quite like STL, but they're along the same lines as STL. Except now we're going to come up with a way to make it so we can select at runtime which one we want to choose. Except the rule is you can't go back and modify anything with the existing implementation. You can't change AQ, you can't change LQ. You have to keep them exactly the way they are. And yet somehow you have to make them work in an environment where you select at runtime. And of course, this has to be very clean and so on. Well, it turns out the solution there is the adapter pattern. And the way this is going to work, let me just go over it real quick. If you go here, you should find the shells, which are here on the line. And we go to assignment 4. Oops, assignment 4A. All right, so there's assignment 4A. And here's the main test program, which will undoubtedly change as we get more test stuff done. The bottom line is the main interesting thing takes place down at the bottom. You come into the program and you give the program a command line argument that says whether to use LQ or AQ. So this is selected at runtime. And we use a factory function called makeQ to make the appropriate kind of queue. Here's the factory function. If you ask for LQ, you get an LQ adapter. If you ask for AQ, you get an AQ adapter. If you get SQLQ, you get an SQLQ adapter, and so on. All of these things are queues. We'll look at what a queue is in a second. And then the main program comes in here, irrespective of what kind of queue you asked for, whether it's an AQ or an LQ or an STLQ or whatever. The same exact code is used. So we say queue front, queue NQ, queue is empty, queue DQ, blah, blah, blah. You're programming with these queues in a polymorphic way. So remember we talked about polymorphism before? So we're using these queues polymorphically. We don't know, we don't care in the bulk of the algorithm whether or not these things are done with AQs or LQs or STLQs or some other kind of queue you might want to implement. So that's all done in a generic way. And it's the factory that decides what things are going to be done. But keep in mind, you can't change your existing queues. Those have to stay identical. So the way this is going to work is we're going to have something called a queue adapter, which does a very cool little trick. The queue adapter defines an abstract base class called queue that's parameterized by the type that you're going to work on. And it defines methods like NQ and DQ and so on. And that part is all pure virtual functions, so there's no implementation. And then we have something called a queue adapter. And a queue adapter is a queue that takes in the type we want and a queue container, like LQ, AQ, some other kind of queue. So what you're going to do is you're going to parameterize the queue adapter with the queues that you've developed, plus another one you have to write to make STL work with your model. And then the adapter is going to do the transformation between something that doesn't have virtual functions, namely your stuff, or STL, and something that expects virtual functions, namely the program that wants to decide at runtime. And so you'll have to come in here and you'll have to fill in the implementation of this thing. It's a one-liner. It takes a while to figure it out, but once you get it, it's really simple. And then here's the implementation. Again, most of these things are sort of just a couple lines of code. There's a little bit of tricky stuff having to do with exception handling and so on. But the point of all this stuff is to understand the pattern and to recognize by using these patterns, you can have very, very little code that you write, and yet you can do very powerful things. You can take stuff that was not intended for use in a dynamically bound environment, and you can use it in a dynamically bound way, which is really cool. So that'll be the first part of the 4-part assignment. Yeah?
So when you're saying pattern, you mean using line second?
No, pattern as in the gang of 4 patterns, as in the bulk of the course, which is on patterns. So this is the book. This is where we'll be focusing on. Gang of 4 patterns. This is the book. And so that's the book where everything's going to come from. The adapter pattern is a pattern in that book, and you can read about it online. Or you could also learn about it online. A lot of the stuff we're going to be talking about here, just to remind you again, I think this is covered on Piazza somewhere. Lectures for many of the things we're going to cover are actually part of my Coursera course from last year in the appendix. So a lot of the things we'll talk about are actually related there. So those are good videos. If you're done with your assignment early and you're bored, spend a little time watching some of those videos. We'll start talking about all those patterns soon. Other questions? Okay, quiz Wednesday. Think about what an adapter is.